Okay, so we're now going to look at how you actually find out delta H value. So let's say you were doing an experiment in a classroom. How on earth would you work out the delta H value? So if we pick the reaction of, let's do methanol being burnt in oxygen to make carbon dioxide and water. So let's say we were asked to work out the enthalpy change for this particular reaction. So it's a combustion reaction. So we're burning 1 mole of ethanol completely in oxygen to make carbon dioxide and water. We need to balance the equation, so we'll have a 2 here, and 1, 2, 3, 4, and 1.5 over this side. So we've been asked to work out the enthalpy change of combustion for this particular reaction. So I have found a question that has this as already set up, so we'll use this question. So here's the question. It says a spirit burner containing methanol is used to heat a sample of water. And you've got the mass of the spirit burner before and after. You've got a volume of water, we've got an initial and a final temperature of the water, and then the density. And it says write an equation to express delta CH, so enthalpy change of combustion for the reaction, which we've already done here. So that is an equation that expresses the enthalpy change of combustion for the reaction. And then it says calculate the enthalpy change for the reaction using this data here. So how on earth are we going to use that data to work out the enthalpy change of the reaction? You can use this equation. So Q is M times C times delta T, where Q is the heat energy. So heat energy, and it's measured in joules. M is the mass of the liquid heated, so the mass of the liquid that gets heated up in grams. C is the specific heat capacity of the liquid that is heated. So in this question, the liquid being heated was water, but we'll come back to that now. And then the final term there, delta T, is the change in temperature in Kelvin. So we can use this equation along with this data here to work out the energy change for the reaction. So let's talk a little bit about what they've actually done. So they've put the methanol into what's called a spirit burner, into a container, and they've set it alight so that the methanol is being used up, it's burning in oxygen, and it's releasing heat energy to the surroundings. We're assuming that all of the heat energy is being transferred into the water. So we assume in this sort of setup that every bit of energy that's released by this reaction is put into heating up that water. So if we look at the data, we've got the mass of the spirit burner before we start burning it, and after we start burning it. So if we've got the difference in this, we'll have how much fuel was used. The volume of water used is 150 centimeters cubed, so 150 milliliters. And it says for water, the density is 1 gram per centimeter cubed. So for every centimeter cubed is 1 gram. So that means I got 150 grams of water in there. And then I've got the initial temperature of the water before I started burning and the final temperature of the water. So in essence, I've got a change in temperature here. So if I put that there, we'll work out these values. So if we work them out individually to begin with, so M is the mass of the liquid being heated. So we've got two liquids, we've got the fuel and we've also got the water. We're concerned with the liquid that's being heated up, so the water. And we worked out before, for the volume of the water is 150 and the density is 1 gram per centimetre cubed. the mass of the liquid being heated is 150 grams. C is the specific heat capacity of water. If you look on your data booklet, you'll see that it gives you the specific heat capacity of water. So specific heat capacity of the liquid being heated, which in this case is water. And I think, let me just check. If you look on the front of your data booklet, you'll see that it's 4.18 joules per gram per Kelvin. So it's like that. And it says specific heat capacity of water, so 4.18. Delta T is the temperature change in Kelvin. And you'll notice that in the question, they've given it to us in degrees Celsius. So if we talk a little bit about that, so the temperature at the start is 21.5 degrees Celsius. Temperature at the end is 62.5 degrees Celsius. If we change those two to Kelvin, so we add 273 to each of them, this one gives us 294.5 Kelvin, and this one also will give us, let's just do that quicker on the calculator, 335.5 Kelvin. So we're going to work out the change in temperature. So the change in temperature in Kelvin, 335.5 minus 294.5 gives you 41 Kelvin. Now, I did it the long way, so I did it by converting the units to show it needs to be in Kelvin. But actually, because we're doing a change in temperature, we could just do the difference between these two numbers, because in each case we're adding 273. But overall, change in temperature is 41 Kelvin, so 41 Kelvin. So we can now work out Q. Q is 150 times 4.18 times 41. So that gives you 25,707, and because we've put the units in properly, we know that the units for Q is joules. If I wanted to convert this into kilojoules, I can divide it by 1,000, so 25.707 kilojoules. So what does that actually mean? That's telling me that in burning that much fuel, whatever that amount of fuel is, in burning that amount of fuel, 25.707 kilojoules of energy are released to the surroundings, in this case used to heat up the water. If I want to convert it into kilojoules per mole of fuel, so kilojoules per mole of fuel, and standardize it, then what I'd need to do is take that value and work out how many moles of fuel were burnt to release that 25.707. So the difference between these two numbers, if I work it out now, 196.97 minus 195.37 gives me 1.6 grams. So 25.707 kilojoules of energy released when burning 1.6 grams of methanol. So that's how much energy is released for burning that much methanol, and I want to convert it into kilojoules per mole. So if I can work out how many moles of ethanol that is, which I can do, so number of moles is the mass over the MR, 1.6 over MR of methanol, so 12 plus 16 plus 4, 32. So 1.6 over 32 will give me 0.05. So now I know that 25.707 kilojoules of energy is released per that many moles. If I do that number divided by that one, which I will do now, I'll get it in kilojoules per mole. So 25.707 over 0.05 gives you 514.14 kilojoules per mole. So for every mole of fuel that's burnt, that's how much energy gets released. Now I'll just take it into the context of my enthalpy change. The enthalpy change for the reaction in kilojoules per mole is 514.14 kilojoules per mole. And I now have to think, right, is this reaction exothermic or is it endothermic? Because if it's exothermic, this value needs to be negative, and if it's endothermic, the value needs to be positive. How can I work that out? So if you look, the fuel is releasing energy to the surroundings, it's causing things to get hotter. So this is therefore an exothermic reaction, and the enthalpy change is therefore negative. So the answer to that question is that there.